Welcome back, ladies and gentlemen. This is Mark Anderson for Keller Community College, and we're going to talk today about inverses of functions. And we're going to kind of give away in this first 30 seconds. An inverse is where it's either a mathematical opposite or it's where we switch x and y. And I'm going to go in depth into all kinds of inverses that you've been using up to this moment in your algebra career. You've probably done a lot of inverse operations. But what we're going to do today first is we're going to talk about the inverses of functions. And it's probably best to kind of go back to talk about what is a function. A function has a pretty clear restriction on it. For every x, there is one y. And for every x, there is one y means that if your formula or if your equation has this property that there is only one value for of y for every x value, then this is something you can plug into your graphing calculator, because your graphing calculator is a function calculator. And the test for this is the vertical line test, or the VLT. The vertical line test means that if you can draw a vertical line and it only touches one part of that line at one spot, or if you can imagine one pixel on a computer screen, then it passes the vertical line test. But a circle would fail the vertical line test because a vertical line would hit the circle in two different locations, all over the place, from east to west on this, or left to right. A loop also, like if you imagine a corkscrew or a roller coaster, or if you're looking at the Maverick at Cedar Point, where it has a greater than 90-degree curve, that vertical line would create a dollar symbol, but it would violate the vertical line test. A parabola that opens up sideways, like so. I think we're going to be seeing some of those in the next chapter as we look at inverses of roots, so to speak. And also a vertical line violates the vertical line test. So these are 5 examples of non-functions. But we also have some functions that are also possibly one-to-one. And when a function is one-to-one, so let's say it passes the vertical line test, a function can be one-to-one if it basically has, for every y, there is one x. For every y, there is one x, which means that the horizontal line test will be a way to check to see if a function is one-to-one as well. So you have all of these different, different patterns, and some of them are functions, and then a subset of those functions are functions that are one-to-one. These are functions that pass the horizontal line test, and the horizontal line test is another way of saying that if you go from left to right, that your horizontal line would only touch one pixel on that computer screen. Now a circle still fails the horizontal line test, and so does a loop. And this, however, as you see, it doesn't fail the horizontal line test. It would fail the vertical line test, but it wouldn't fail the horizontal. So if I made a side view of a roller coaster like so, that would fail the horizontal line test. And so with this open-ended parabola, and same with a downward opened parabola. This horizontal line is, or vertical line is okay, but an example of a non-one-to-one function would be a horizontal line. A horizontal line fails the horizontal line test. So now we're going to get into these 4 pictures here, and I'm going to say, like, for each function, you're going to determine, because these are all functions, you could type them all into the graphing calculator, you have to determine whether they're one-to-one, and if they're one-to-one, you have to find the formula for the inverse formula. Now, at this moment, you may wonder, like, why do I need an inverse formula? And the short answer to that is that you'll need it for logarithms, because a logarithm is the inverse of an exponential. But in this section, what we're going to do is we're going to have some fun actually looking at a linear formula, and we're going to find its inverse and prove that it's an inverse as well on the next page for a specific cases, not for all cases. So what this is going to be is a function of 2x plus 8, and if I graph this, because part A says determine whether it's 1 to 1, so if you did graph it, it would have a y-intercept of 8 and a slope of up to and over 1, so it would look like this. And that, my friends, is definitely going to pass the horizontal line test, so yes, it is 1 to 1. Now, if it is 1 to 1, find a formula for the inverse, and this is a two-step operation. The first thing you do is you're going to switch x and y. You're going to switch x and y, so this equation, which is usually y equals 2x plus 8, it's now going to be x equals to y plus 8, and then you will solve for y. And by solving for y, you're then going to get a new equation, which will then be the inverse of the first equation. So now that I've switched x and y, I am now going to move things around. I'm going to subtract the 8 from both sides. I'm then going to divide by 2. So this is going to be x, or 1/2 x, minus 4 is equal to y. So I divided everything by 2. You could have written x over 2, but I prefer to have the 1/2 in front of it for those of you familiar with slope, rise over run. Now my final answer, I'm going to write that my inverse function, oh look, new notation. The inverse function of x is going to be 1/2 x minus 4. All right. And a lot of times I get students who don't understand the material or try to fake me out a little bit on a test or a quiz. They try to say, oh yeah, the inverse is 1/2 x plus 1 over 8. But look at the y-intercepts here. They're not actually patternable like the slopes were going to be. I mean, take a look at this problem. First, we're going to figure out if it's 1 to 1 or not. The y-intercept is 2, and this one goes up 1 over 3, and this passes the horizontal line test. So yes, it is 1 to 1, and therefore, since it is 1 to 1, it has an inverse. And that's actually one of the criteria of having an inverse. 1 to 1 functions have inverses. 1 to 1, if the function isn't 1 to 1, then it doesn't have an inverse because it would then break the law of a function. So what I'm going to do is just put my y in 1/3 x plus 2 here. I'm going to switch my x and y position, and there it goes. And then I'm going to get the y by itself, subtract the 2 from both sides, and then I'm going to multiply by 3. Multiplying by 3 is the best way to get rid of division of a third because this is a third as big as y, so if I triple everything, this becomes 3x minus 6, and tripling 1/3 y is going to be just y. And if you want to see that step written out, you just multiply everything by 3 here and 3 here. 3 times 1/3 is 1. Bam, bam. So now I have this. My final equation will be written like this. The inverse of the x equation, f of x equation, is going to be 3x minus 6. So again, you said, oh, well, I found the pattern in the slope, but look at that y-intercept. That's something right there. You don't actually have like an instant connection, and I strongly warn you about this third problem here if you're trying to look for a pattern. Just you're better off checking to see if it is a function, which in this case it is, or it's 1 to 1 because it does start at 7. If this went to 10, that would be right there, and this goes down 1 over 1, like 45-degree angle on most graphs where the x and y are the same unit, spacing-wise. So yes, this is another 1 to 1 function, so it has an inverse. So my y equals 7 minus x is going to now be x is equal to 7 minus y. I am then going to move the 7 to the side. X minus 7 equals negative y. Then divide everything by negative 1. So negative 1, negative 1, negative 1. So that means I've got negative x plus 7 is equal to y, or the inverse function of the original function is negative x plus 7. Now, I want you to look at that. Negative x plus 7, and this is 7 minus x. Holy smokes, the inverse function is the same as the actual function. Like, that's kind of cool. And actually, there's going to be more information about inverses in the next chapter that I'll teach, so you can see some geometric relationship between a function and its inverse. Spoiler alert, it's a reflection over the y equals x line, but I'd rather really explain that all in a separate video rather than trying to put it into this longer form video. Now this is y equals 8, and that is a horizontal line, and that does not pass the horizontal line test, and therefore this does not have an inverse. So yeah, that's the end of that. If you find a function that doesn't have that isn't one-to-one, then you can't get an inverse. So let's kind of go to the next page and really reinforce that fact. It says it actually in the notes that I typed up here for this worksheet. It says if a formula is one-to-one, then it has an inverse function. Okay, cool. This is like, because I told you that you have to check to see if your functions pass the horizontal line test, and these definitely do. Now it says if an inverse function, it's like an inverse operation in the idea that it takes us back to the original value of x. Now for me to explain that a little bit more, I'm going to kind of go up a little bit into the margin of the paper, and I'm going to create a table. I'm going to create a table, and the table is, if I have addition, what is the inverse of addition? And the inverse of addition is subtraction, and the inverse of subtraction is addition. And I would know that because if I do an inverse operation, let's say I'm moving stuff away from this x over here, this 3x plus 4 is equal to something like, 19. The inverse operation of addition is subtraction. So this little thing that you're doing to balance the equation, this is an inverse operation. And this inverse operation is going to give you a simplified problem. Now, addition has an inverse operation of subtraction, and subtraction is addition. But what do you get when you do inverse operations with addition or subtraction? Well, you get 0. We don't usually write the 3x plus 0 equals 15. In fact, many students just say, oh, it cancels, and then just, doesn't draw a single thing down there. But you technically would get a 0 if you use the inverse operation of addition and subtraction. Well, what about multiplication and division? What about that? I mean, because the inverse operation of division is multiplication and vice versa. Well, now if I divide both sides by 3, I get an answer of x is equal to 5, but it's technically not x. I mean, 3 divided by 3 is 1, but even I emphasize in my class we would never write our answer with a 1 in front of it, even though 3 divided by 3 is 1. So when you multiply and divide by the inverse, you actually get a 1, and most students just say, oh, it cancels out, but it's 1x, and then that can be simplified just to x is equal to 5. Now, in a couple chapters ago, we explored the idea of what happens when you have the square root of x. What is the inverse operation of square rooting? Well, it would be squaring, and vice versa. If you had a square of some number and you decided to take the square root of it, that would give you x. And an example of that is the square root of 6 squared, because 6 squared is 36, and the square root of 36, if we're assuming that all values are raised from positive numbers, is going to be 6. The other way around, if I had the square root of 6 squared, this would be taking the square root of 6 twice, which is then the same as the square root of 36, which is 6. Or the decimal approximation then squared would then give me an answer that could be approximately 6. So what we've seen is that the inverse operations of addition and subtraction give us 0. The inverse operations of multiplication and division give us 1. The inverse operations of square and square rooting give us x. Well, you see all this formula stuff here? This is to say that the inverse of the inverse function of the function will give us x. So the function of x and its inverse, these are the opposites here, is going to give me x, just like it did over here. So that's what this is saying, and the order doesn't actually matter, and as the order didn't necessarily matter in my table up here, where addition and subtraction will give you 0 and vice versa. So what we're about to show is we're about to show the inverse of the composition of the function, the composition of the inverse function property to determine whether the functions are inverses. So what I'm going to do, and I strongly recommend that you watch the video on compositions that I did right before this one, is that we are going to plug the g of x equation into f of x and see if we get x, and vice versa. So what I'd like to do, and that's what this equation is saying up here. Now this is an equivalent way of saying it, the inverse of f of x is the same as the inverse of f of x is equal to x. I mean, the notation is going to mean the same thing depending on the book or what you're using there, but to us, what you're really caring about is like, what am I going to do here? Well, you're going to plug g into f and see if the answer is x, and then you're going to plug f into g and see if the answer is x. So I would take your pen or pencil, and if you're using this worksheet, I draw a line in half, and if you have your homework in front of you, you're going to have two parts for each problem. You're going to show that f of g of x is equal to x, and you're also going to have g of f of x is equal to x. So the first thing I'm going to do is take my g of x equation, so g of x is equal to negative 2x. I'm going to plug it into my f. So every single instance of f, this f of x is not going to be f of x, it's going to be f of negative 2x, and that's going to give me negative 1/2, parentheses, 2x with the negative in front. So this negative 2x went in for that x, and if I simplify it, it should give me just an x, which it does, because negative 1/2 times negative 2 is positive 1, x. So this is f of g of x. Now I have to try it the other way to make sure it works. Maybe I'm going to made a mistake this way, so it's best to check it the other way. So I start off with my f of x, which is going to be negative 1/2 x, and I'm going to plug it into g of x. So g of x, which is now negative 1/2 x. Sorry, that's so sloppy. Yikes. All right, so g of negative 1/2 x is going to be equal to now the negative 2, and then parentheses, negative 1/2 x. And that means I'm going to multiply these two together, which negative 2 times negative 1/2 is 1x. So g of f of x is now equal to x. So now I've shown that both are true, so I've satisfied this and this condition in both directions. Now the last two problems we're going to do today, again, I think it's best to kind of split your paper in half, and on the left half we're going to go f of g of x and see if that's equal to x, and then we'll go g of f of x and see if that's equal to x. So I'm going to take my g of x, which is this equation. Now I'm going to write a little bit less this time. I'm going to plug that in for this x right here. So this is going to be 6 times the quantity of 1/6 x minus 5/6, and that's going to be then adding, I'm going to add 5 to that, because this 6 and the 5, went here and here, and that expression went inside the x. Now my hope is that this would give me an answer of x, and it actually does, because if I distribute the 6 times 1/6 x is just 1x, 6 times a negative 5/6 is just a negative 5, plus 5, your answer is x, because the inverse of these makes 0, so my f of g of x, my f of g of x is equal to x. Now here I've got my g of f of x, so I'm going to take my equation, and notice that since I've written all over it, I'm going to now clear it so I can write all over it again. So again, sorry that the left half got erased, just back up the YouTube video, right? So now I'm going to go I did my f of g of x, I'm going to go g of f of x. So I'm going to take the 6x plus 5 and plug that into the x right here. So I've got 1/6 times 6x plus 5 minus 5/6. So I do my distribution here and here. 1/6 times 6 is just 1x. 1/6 times 5 is going to be 5/6. And then I got the minus 5/6. That simplifies to 0. So g of f of x is equal to x. So if you have to, in this section, show the inverse function, and kind of do that little example of g of f of x and f of g of x, just split the paper up and follow my pattern there. It's pretty straightforward. Just keep your positive and negative straight, and you should be able to get an x for any of these to test whether or not f and g are inverses of each other. All right, well, thank you very much for watching. I will talk to you soon.